Okay, the microphone's working. Hello, I'm Charlie. So we have a talk about std format, and before we get into it, I just want to highlight that a bunch of people from the Visual C++ team at Microsoft, including myself, are here this week, and we have a channel on the Discord, and we also have a survey about our tools that if you use our products, we'd appreciate it. Feedback is good. So this talk has two parts. We're first going to go over what std format is and briefly how it works, what it looks like when you use it. And then we're going to dive into some of the internals. And we're basically going to talk about the kind of front end part of format, everything that happens between when you call the initial function that's specified in the standard to when we're done parsing the format string and we actually are just formatting each argument. We're not going to talk about the particulars about the mechanics of like how we convert a float into a string or anything like that. We're going to talk about how we get your formatting arguments and the specification of how you want to print them, how we get that from, you know, the call to std format into the said mechanics of actually converting stuff. And that part is going to have quite a lot of code, but hopefully some of it will be relevant to you if you write similar generic libraries. So yeah, let's get into it. So format was added in C++ 20, and it's a new text formatting facility. And it's based on the relatively popular libfmt library, but some features are removed, and some things are changed very slightly to make it fit into the standard. Yeah, that library is inspired by Python's stir.format method, among others. So if you've used that, it'll be similar. You can call, it takes a format string specifier and parameters to format, and it puts the parameters into the string and returns the formatted string. So you can just insert stuff. You can, after a colon, in the replacement field, you can specify various options. So here we've said, we would like this to have width 6 and be center aligned. And when you align it, you're going to use asterisks for that. And for the numeric knobs in the specifiers, you can specify those dynamically like you see here. We're saying, this time we're saying we want the alternate representation, which is how we get the OX and hexadecimal prefix, and then we want the width to be dynamically specified, and then we pull that in from another argument. There's various other stuff you can do. Yeah, there's a large variety of format specifiers. There's also new specifiers in C++ 20 for the calendrical and time types in the chrono header. So unlike sprintf, format is type safe. The worst thing that'll happen if you screw up your format string is format will throw a std format error. And that'll mostly happen if you're using the std vformat functions, which can be used for a runtime format string if you're doing localization. It's faster than sprintf. It's also faster than IO streams, much faster than IO streams. In our implementation, you need to compile with /UTF-8 to see major performance improvements. We're working on that for people who need other encodings. If you're using the wide versions of format, things are great. You don't have to do anything special, it'll be fast. It's available in MSVC in Visual Studio 2019 and 2022 under STUD C++ latest. We're going to talk about the plan to bring it to STUD C++ 20 at the end of the talk. And you can see just how much faster it is than the alternatives. This is against our version of IO streams and our version, the UCRT version of SNPrintf. Yeah, it's a lot faster. And we get that performance partly by SNPrintf and IO streams not being, SNPrintf having some inherent limitations that make it slow, and IO streams, both parts of how you customize it make it a little slower than it has to be, and our implementation has some choices some performance choices that don't make sense anymore. But the big reasons why STUD format can be faster is that it's specified to use charconv for floating point conversions, and charconv is very fast. It's very, very fast. It's not quite the world's fastest floating point to string function, although an implementation could use the new algorithms that have come out since we implemented it. STUD format's a lot easier for the compiler to inline, especially than IO streams. There's no virtual calls for the common types. There's no indirect calls at all for the common built-in types that you'd want to format. If you use the customization facilities, that does introduce some indirect calls. It doesn't interact with locale at all, unless you use a specifier that specifically opts into that. This is nice. That means that when you're writing code using STUD format, you know that the output will be what you're actually seeing. You're not going to end up in a situation where somebody has a different locale set and the output's wrong, and oh, you're formatting into a fixed length buffer, and now you've written all over your stack. Uh-oh, that's not going to happen. You have to explicitly opt in, and that means that we don't need to construct a locale. We don't need to look through, shuffle through your facets. It makes things a lot faster. Format does not interact with erno. SPrintf and SNPrintf don't necessarily have to interact with erno. But the common implementations do, and I believe POSIX requires it. And erno, of course, is it's a global thing. So interacting with it can cause problems. There can be contention on erno. Format also has way better support for positional indices. If there's something you want to copy into a string multiple times, you can just pass it in once and say, replacement 0. Some versions of SPrintf support this. However, if you pass a bunch of arguments to it and then you try and use the positional argument support on an argument that had to be passed on the stack to SPrintf, the implementation of that is a bit of a nightmare. And that can make SPrintf really slow. So that's just the basics of format, why you want to use it. It's great. It just works, basically, and it's very fast, and if you've used Python before, it'll be very familiar. And so let's get into some of the nitty-gritty of how we implement format in MSVC. Our implementation is based on libfmt. The Microsoft standard library is open source now. This was one of the, C++ 20 was the first standard revision where major features were developed in the open source repo, and one of the things that we did was our license is compatible with libfmt, and so we can use the techniques that library does, that library uses, and we can just use those directly, and we didn't have to rediscover them. That said, We don't ship libfmt. Our implementation is distinct, and it's maintained independently by us. While the structure of the code is similar, the data structures are not exactly the same, and it's not, you're not going to find the exact libfmt code in our headers. So all of the things that format needs to do to be fast and to work at all involve some kind of type erasure. That's basically the entire path from calling std format to ending up in underscore write float to output iterator is all just doing various kinds of type erasure. And so that's a lot of what this talk is going to be about. And if you're not familiar, type erasure is anything that removes type information from the visibility of the compiler. And it's usually used if you're passing that around, in some other way, or you need really detailed control over how things are stored, that sort of thing. If you need to store heterogeneous types, you can make an abstract-based type and store pointers to that. If you need to allow different types to be manipulated with the same code, and in general, in this whole talk, when I talk about like the same code, I'm talking about like assembly, like the generated code from the compiler, not the same C++ template function. So I basically always mean the exact same generated code. And because of it allows you to use the same code, it can reduce code size substantially, which is a lot of why format needs to use it. And you can use it for extension, like we do with just regular old virtual base classes and virtual functions. Format uses type erasure for everything under the sun. We need to store the arguments you pass in a collection. smprintf needs to do this too. smprintf, unfortunately, doesn't get to choose which data structure it uses. It gets to use the stack. That's the data structure you get. But we get to choose. We need to allow the collection of arguments to be manipulated with the same code, because we need to parse your format string and interact with the arguments to do error checking, to pull, for the whole functionality of format. And because of that, if we don't do any type erasure and just pass things through, we'd have to, every possible combination of formatting arguments would result in a duplicate copy of all the formatting code. It would not be fun. We also need to reduce, a similar problem happens with the output iterator type that you're formatting into. And we use similar techniques for that. And then if you customize std format using the specialization of std formatter, which we'll get into briefly a little later, we need to, we can't know beforehand all of the possible customizations you could do, so we need to be able to call your customization in a totally generic way. There's different ways to do type erasure. The standard library has a bunch of them. Also, if you've ever used scripting languages, there's basically, like, they just have a standardized way that they do this. Like PyObject is a tag union. And you see that in Python, in Ruby, and in any of these languages, essentially. The standard has variant any function and various other types that involve erasure. Variant and any are the two most direct. Lots of uses of virtual functions. If you've ever used the Pimple idiom, it's the same idea. You're making it so the compiler doesn't really have to know as much about your code. So to understand exactly where we use these techniques, we need to understand a little bit of what happens when you call format. So there's a bunch of std format functions in the standard. They're all implemented in terms of v format too. There's also wide versions of all these functions. In this talk, I'm ignoring them, and I've removed a lot of character type parameters for brevity, basically. But if you want to do wide strings, that's fine, you can do that, it works. So all the format functions are implemented in terms of this one function, vformat2, and it takes an output iterator, a format string, and a string view. That type has changed a little bit with some of the defect reports that have been voted into the standard, but we'll get there. And then it takes this format args parameter, which is a new type that the standard specifies. And it says, all right, this is the actual full type of format args. The important thing to notice here is that format args depends on the back insert iterator. And you'll notice that that's a format buffer. That's not the output iterator. We'll get to why that is. Originally in C++20, when format was first voted in, this didn't last long, but the standard actually said that format context was back insert iterator of the output. And it would be different for each call to vformat2. That didn't last long. It was a problem. We'll get into why. So vformat2 does two things. Constructs a format handler, which is a bunch of callbacks. That's it. It's not a virtual class or anything. It's just a class with methods, and the methods serve as parsing callbacks. And then it passes that to parse format string, which parses the format string. And again, the important thing to look at here is what types these functions depend on. Format handler depends on the type of the output iterator, the format string type, which is string view or wstring view, and the format args, the args type. And then parse format string depends on the full type of that handler. So that means that every time the output iterator type or the type of the formatting arguments changes, we're going to emit, it'll be a new template specialization for all of the parsing code and all of the parsing callbacks. That's not all the code in std format, but it's a large percentage of the code in std format. So it's a lot of code, and we need to avoid that if at all possible. Which is why we can't just have format handler be have a variadic template parameter and forward the arguments directly through. It would be too much. So we need to, and it's also why we do this format buffer thing, which again we'll get to later. But that's the arguments are by far the biggest thing that you must type erase, or you're just going to generate an absolutely enormous amount of code. And so the standard specifies essentially that you must provide some kind of type erase data structure for these. I suppose you could forward all the arguments through and kind of fake it and return the basic format args at the last minute if you really wanted to have an implementation that generated a completely absurd amount of code. But so what the standard says is that the data structure is just going to be a variant of all of the basic built-in types, and then this handle to a user customized type. And you'll notice, all right, well, variant's a tag union. So it's going to have the tag, and then it's going to be, the union itself will be as big as and have the same alignment as the biggest and most aligned type in the union, respectively. In this case, string view and handle are both probably 2 pointers big, and are both probably aligned on the same alignment as a pointer. And then it has the union discriminator tag, which I suppose could be smaller than a pointer. However, the standard then says format arg store and basic format args is going to be an array of basic format arg. So even if the handle, in our implementation, I think it is a pointer size, but even if it was smaller, it doesn't help because the whole thing has to be aligned. And so basic format arg in the standard, this is 3 pointers big for everybody. How nice. On a 64-bit platform. So that's a little unfortunate. And the standard says, you know, when you call, there's a function make format args that in the call to that, it constructs this format arg store, and the standard has dashes in it, which indicates that we don't have to actually expose a type called format arg store. It's just, it's expository. And then that's immediately converted into basic format args, which is what you saw passed into v format 2. And that's just, it just pulls out the size and stores a pointer to the array, that's all. So having 3 pointers per type, you know, it's better than generating combinatorially more code, but it's not great. We don't want to do that. And actually, initially, I was just going to do that and then benchmark it because it's good to measure stuff. But before I got there, one of our contributors saw this and was like, and also because I figured that the use case where you store the basic format args for reuse later would be pretty uncommon. But one of our contributors saw that and he's like, well, in my company, like we've been using libfmt and like we store those all the time. And like, this is like the data, like this particular data structure is kind of optimal for us. And, you know, he implemented the whole thing. So a big shout out to Misco, and it's been great having people jump on stuff really early and implement exactly the thing they need. So huge shout out to our contributors all through the talk. But so in MSVC, we can save some bits here and do it a little better by basically going from an array of these of variants, an array of structs, to a struct with 2 arrays in it. This is a common thing that you can do if you have padding problems and you need to save some space that is otherwise just going to maintaining the alignment of your types. This is an effective strategy to combat that. So we store an index which consists of the union tag and then also an offset into the storage, which is stored all compacted. So if it's a character and then an int and then another character, it's going to be, you know, the first byte is the character and then the next 4 are the int and then the next one's the character with no padding. And then when we convert to format args, just like before, we pull out the size and then just store a pointer to format arg store. We actually store a pointer to the first member just because of how we have to access things, but that saves us an arrow operator when we're when we're extracting the data here. And then the index is just one pointer size, and we just pack the type into 4 bits in there. This does mean on its size t, so if you build for x86, format supports slightly less total arguments than on x64. However, this would be passing in hundreds and hundreds of megabytes of individual arguments into format, and it would probably be like thousands of individual arguments. I wouldn't do that. If you put all of that data in a container, you can format it great. So that's the structure of just how we store the arguments. You'll notice that basic format arg itself doesn't show up there at all. And that's because we create that on the fly when it's needed in the parsing code. And so this is something that many uses of variadic functions in C++ may want to do. Basically, it means that you only get kind of duplicated code gen for the initial function that is variadic, and then you pack everything into some structure. You don't have to forward everything along. You can make programming a little easier because you don't have to worry about, you know, perfect forwarding or, you know, losing CV qualified. Well, you do when you write the type erase container, but after that, you don't. It doesn't really gain us much in performance because we really have to do this. And if we didn't do it, then the data structure we get is again like the stack. But it is nice that we control it because we don't have to use the stack data structure. Note that while a lot of times people associate type erasure with allocating memory on the heap, none of what format does that. It's just pointers to the caller's stack. So the next thing we're going to talk about, also in terms of code size, is that FMT buff, which is the output iterator type. And again, this is the implementation of vformat2, just with the format handler stuck into the parameter list. And you'll notice that all the parsing code depends on the type of the output iterator. So that's a shame. So if you have a program where you're formatting into multiple different things, say a string and then a vector, we generate a lot of extra code. So again, the standard initially specified that we had to just pass in the output iterator type here. We didn't have a choice. We did what the standard said. And every additional output iterator type you used was about 30K of additional code that would end up in your executable. That's not great. And it's a pretty severe issue. P2216 is the name of the paper that fixed this, as well as adding some more safety, compile time safety features. And that was adopted as a defect report for C++20. So we need more type erasure. We need to avoid making all of our parsing code dependent on the output iterator type. And we do that by making our own container. We make a special container, and that's what FMT buffer is. All the underscores that you see here is just because this is standard library code, and we use reserved names to avoid clashing with our users. So double underscores and an underscore followed by a capital letter. If you're writing include guards, please don't write them with an underscore followed by a capital letter. Anyhow, format buffer has the usual containery things. Some data, size, and a capacity, and has pushback. You need pushback for output iterators. That's kind of what they do. And then it has a virtual function called grow. And that's where that'll go and do the meat of what you need. And the reason we need a size and capacity is because that way pushback doesn't have to call grow every time. You only have to call grow when your size is bigger than your capacity. So this is the implementation. This is what actually happens. This is a derived class from format buffer that we construct immediately in vformat2, and we'll see that later. Stores its output iterator, small fixed buffer, and all grow does is it says, have we written more than the size of our fixed buffer? And if we have, it's going to call this flush function, which goes and does the, which actually writes to the output iterator. And then once it's done with that, it goes ahead and sets size to 0 and capacity to 256. And we can continue on our way writing. So to flush, we have another another slight optimization here that's fun, where normally what you do is you just copy from your little fixed size buffer into your output iterator. Unfortunately, that calls pushback every time, which means that the container, if the actual underlying container needs to grow, it's probably going to double in size or something. It doesn't know exactly how much it's going to need to grow. And it also means that especially if you're in debug mode, all of our additional safety checks with our iterator debugging feature are going to happen multiple times, which isn't great. So We specialize this function for basic strings and vectors. There are several other contiguous containers in the standard library that we probably could optimize for, but strings and vectors are the real important ones. So we just check if, so we get the container type from the output iterator. That's using just template argument deduction to get that type. We check if it's one of them that we support. And if it is, we pull the container out of the output iterator. This is using the usual, there's a common trick with output iterators. You write a class that's derived from output iterator, and then you can make the container public, because the container is a protected member. So we do that, and we just insert. Otherwise, this last line here is just outputting into the underlying container. This optimization was also initially contributed by an open source contributor, and the final version that is shipped is a little bit different from the full optimization that you can do. One thing that, if you're writing your own format library, depending on your opinions on things, you can use this optimization for like anything that has an insert method. But in the standard library, we're not really allowed to do that. We can't just look at a user insert method from some random user provided type and say, oh, that must work just like the insert in the standard library. It doesn't work like that. We have some other specializations of this buffer class that we use. This one is for if there's a vformat2 function that's a replacement for, that's a kind of direct replacement for sprintf. So it's for formatting into fixed size buffers. And so this just, it's, well, if your container was just a pointer, then we don't need to keep track of the size. We have infinite size because we're just trusting you that you're not going to write off the end. It's what the standard says to do. And yeah, and there's, grow doesn't have to do anything. And if it gets called, you have a problem because you've written larger than the content of your entire virtual memory space into your output iterator, which probably isn't what you wanted to do. So now that we have this special buffer type, we change vformat2. Instead of just calling format handler and parse format string, it's gonna check if we already gave it an output iterator into a format buffer. And if we did, we're just gonna use that so that we don't double wrap it. Otherwise, it's gonna make a new iterator buffer from your output iterator. It's gonna form an output iterator into that. And then call parse format string. And thus, the full type of the output iterator that actually gets used is the same no matter what. And we've kind of gotten performance here too, not just code size. The optimizations we did, I suppose we could have forwarded the full type through and still done many of them. But the performance penalty for that virtual call is really not a big deal because of that small buffer. If you're on an embedded system that can't afford 256 characters on the stack like that, maybe you'd make a different implementation choice. But the erased buffer type gives us a location in which to do all this stuff. We don't have to go through pushback all the time. We can do the optimizations, and it's just every additional output iterator is just a tiny additional bit of code. Because vformat2 does get a different, you're going to generate new code for every type. But none of the functions, all the functions it calls are going to be the same. So it's not a big deal. The last set of tricks in the format front end here is for user-defined formatters. This is what a user-defined formatter looks like. It's got a parse and a format function. You'll notice parse is const expr. Again, in the original C++ 20 specification, It was not necessarily const expr. That was added. P2216 again added compile time format string checking so that parse is now const expr, so at compile time we can parse your whole format string and catch a lot of errors for you right then and there. Not 100% of errors, in particular with those dynamically specified format specs, you can still get into a little trouble. But you're not gonna be able to pass the wrong number of arguments. You're not, in most cases, you're not gonna be able to use the specifiers that don't make any sense, or they're for the wrong type or anything like that. If you do any of that, your code's not gonna compile. This is limited, by the way, to format and format2. The V format functions that take the already type erased arguments don't have this compile time checking. And that's because you really need an escape hatch from this feature. In particular, if you want to localize things. Because for localization, the format string itself is going to be a runtime value. It's not going to be user controlled really, except by their selection of language, but it'll be runtime pulled from some database, from get text or what have you. So in that case, we won't do the checks. Also, if the checks fail, the diagnostics right now are not fantastic. We're working on that, but unfortunately, they're not always great. If you get a compile error in a call to format and you get really bad diagnostics, go ahead and throw the V on there, and then run a test that goes through that path, and you'll get a runtime error that will throw an exception, and that the throwing of that exception is what caused the compile time error in regular format. And so that can be easier to diagnose. You can get a debugger there. And then parse and format are separate because format won't work at compile time in all likelihood. I mean, you saw the type erased format arg structure, right? That's doing a lot of bit blasting into arrays of unsigned char. And just that is a little problematic at compile time. Not to mention, charcom, for example, is not const expr. And you can use formatter to customize format for your types. You can customize both parse and format, although parse has to be const expr, which is a little sad, I guess, since you can't have parse spin up a Python interpreter and run some arbitrary Python code. That'd be fun. But anything you can do at compile time, you modify the string parsing, different notations for anything that comes after that colon. And then for formatting, you can convert to a string however you want based on those specifiers. You'll typically store the specifiers inside as a member variable of your specialization of formatter. And the standard provides built-in formatters that do all the things that format does for built-in types. Those are never instantiated in our implementation when you're formatting a built-in type, but they're there for when you customize stuff and want to reuse things. They are also used at compile time. So I guess they're instantiated, but code is never generated for them. So here you can see this is kind of the prototypical example. You just inherit from one of the standard ones. And the standard one already has parse, so that's out of the way, it's done, you've implemented that. And then you just implement format, and you just call format on from your base class. Easy enough. One of the reasons we don't use the formatter struct at runtime when we're formatting is because the separation of format and parse means that if you do the thing where you can pull in a width or a precision from one of the passed in arguments, we have to pull out the index that you used and store it for later because the parse function of the formatter doesn't have access to all of the formatting arguments. It just has access to the string. So we need to save that for later so that at runtime, you can, or when you're formatting, you can refer to what was previously parsed and pull out the right values. So that's a little bit of a extra thing we have to do that we don't have to do for the built-in types because we just parse and format all in one go. And when we get a customized type, a type that isn't one of the built-in types and that has a formatter specialization that meets the standards formatter requirements, it's a set of requirements much like the iterator ones. It's not a formal concept in the standard wording, but we have a concept that does as much as we can to verify that you meet the requirements. So when you have an argument like that, we store it in basic format args using this handle class, which is a inner class of basic format arg. And it just stores a pointer to the actual value on the caller stack, or I guess if it was on the heap, point there too. And then a function pointer to the thing to do when we encounter this argument. And this underscore format function calls both parse and the format function of the user-defined formatter. And when you call make format args, when we construct the handle type, this is literally the code we use, except with line breaks inserted. We just store the pointer and then we right then and there make a Lambda function that calls the things we need. So this formatter type is us saying, all right, what's the actual type of the user-defined formatter? And then we call parse and we call format. Not immediately inside the Lambda function. And then this Lambda function is called later from within one of the callbacks in that format handler type that we saw earlier. So erasing the user-defined formatter format type is pretty critical. If we didn't do that, we'd get into the same situation as with the formatting arguments, where every time you give us a custom type that we haven't seen before, or if you give us types that we have seen before but in a different order, we'd have to generate all the code again. And we don't want to do that. We want to just use the same code and call a function pointer that does the right things. And because of that, we need to pick an actual concrete representation for these custom arguments that is the same for everybody. Otherwise, aforementioned problems. And the thing where we use a Lambda function in the constructor to pull out these function pointers is actually kind of an interesting general thing that you can do if you have a concept that you would like to store in a real actual object and use like a abstract-based class. You can have a constructor that's constrained on that concept applying and then pull everything out. I guess you can do that without concepts too, but it's, this is something that maybe someday, in a far future version of the standard, there'll be syntax for, but who knows. So the core things that format needs to do to make this facility work is just all about getting from that kind of variadic template call into concrete code that does a specific thing, and everything you passed in is in a specific data structure that's laid out correctly. And so these techniques reduce code size, let you store all of your arguments in the same structure. It lets the same code manipulate them all, and you can do this kind of open extension, which is useful. And I also want to give a shout out for all these techniques to our open source contributors. Huge parts of the std format feature were contributed by people outside of Microsoft into the runtime, and it's been kind of incredible, especially having people basically bring exactly what their requirements are that you kind of couldn't really have predicted beforehand. Having people bring those right to you is really quite nice. And we've also had contributions from Victor. Victor contributed the original implementation of the output iterator stuff, and also is the author of libfmt and did a crap ton of work. Not only did he contribute the implementation, but he also made the implementation legal and worked on getting that defect report through, and he's just done. He's been the driving force behind getting std format into the standard, and he's written a ton of papers, and it's a really quite fantastic library. And right now, there we go. Right now, we're shipping std format in Visual Studio 2019 16.11 and Visual Studio 2022 under std C++ latest. It would be in std C++ 20. However, as mentioned, several defect reports were voted into the standard and have come up. And those defect reports changed some of the semantics and had some ABI implications for format, and some other library features as well. And so we are not going to provide std format under /std C++ 20 until all of those defect reports have been implemented. So that way, you can't get into a situation where you've depended on something that the standard has changed out from under you, and now the ABI has changed, and what are you gonna do? So in an upcoming release of Visual Studio 2022, we'll have the defect reports implemented, and then at that time we'll backport those defect reports into an upcoming servicing release of Visual Studio 2019 16.11. And the features, the C++ 20 library features will be enabled under std C++ 20 in both versions of Visual Studio 2019 at that time. Like I said, std format's very similar to libfmt. And so if you're working on a cross-platform project, you can use libfmt. Right now, msvc is the only implementation of the standard library that has std format. Lots of progress is being made in libc++ as well. I'm not 100% sure of the status of libstd C++ because I don't follow their development that much because for various reasons, but they should hopefully have it eventually. But if you're on a cross-platform project, libfmt is basically a drop-in replacement. There's very minor differences, and it has some additional features. For example, you can pass named arguments into libfmt, which you can't do with std format. And libfmt lets you compile your format strings to gain a little bit of performance. If you are on a cross-platform project, you could use std format on Windows and libfmt on the other platforms, or you could just use libfmt everywhere for consistency and switch everything over to std format at once. So yeah, we're gonna bring this to std C++ 20 in an upcoming release. The feature is currently supported, even though it's in latest. The ABI may change You shouldn't be passing basic format args or any of the new types across ABI boundaries. And there's some pretty big semantic changes in how chrono formatting works, so be careful there. We've only got 1 day left, but enjoy the conference. And as I mentioned, a lot of people from the Visual C++ team are here. And we have a survey. And these are the other talks. And one note, if you are using this, please compile your code with /UTF-8. And it increases performance dramatically. It's over an order of magnitude better performance. Because if you don't use /UTF-8, we don't know what your execution character set is. So we have to assume that it could be one of the ones where we can't just search for replacement fields in your format string. We have to step through the string character by character, because the curly brace byte could be the second byte of a multi-byte character sequence. And that impacts performance quite dramatically. There are, very recently, we now do have a way for the compiler to tell us which encoding we're using. So at least in Latin 1252, which is sort of the default on English systems, we can fix this. But right now, add /UTF-8 to your build system. It'll probably fix bugs that you didn't know you had. And I think now is time for questions.
Hello. So on slide 25, is there a reason why you wouldn't throw an exception inside of there?
Inside of which?
Inside of grow. This is the pointer.
Yes. Well, so grow is only, so we initialize the size, or the capacity, to the maximum possible 64-bit value. So by the time, it's structurally impossible for grow to be called before you have like other like major problems.
Okay, that makes sense.
And in particular, before you like try and write into the kernel's memory. Okay. Theoretically, we probably wouldn't throw an exception from in there. We'd probably put a STL internal assert that says it's unreachable, or just not implement it and just have it call the null function pointer. That's why.
Cool. And I have another comment. You said something about Erno having concurrency. So if you have two threads running with SN printf, I think Erno is actually in thread local storage. So I don't think that there is such a problem, at least for many people.
Yeah, on some platforms that is true. Sometimes it's global. Thread local storage does have some additional overhead in some cases, and Erno also can inhibit certain optimizations as well, because it makes the function have global side effects, which for formatting into some buffer, there's no reason it should have global side effects, right? It only really needs to read the things that you pass into it and write into the thing you say. So yes, there are various implementations of how Erno works, and some of them are less problematic than others. Any questions from online?
We have a few questions from online. First question is there a way to format a container, for example, std vector, with an arbitrary element that can be formatted?
We're working on it. So C++20, that's one of the defect reports, actually. C++20, there's work being done to add the formatting of ranges to an upcoming version of the C++ standard. And vectors are ranges. And so we want to be able to format ranges and also coroutine-based generators. One of the defect reports that we're implementing is a minor change to the signature of format to enable that. In particular, the format in C++20, it's const args ... args, which is problematic for some ranges. Although it does let you format bit fields. They'll be formatted as an integer. After we implement the recently voted in defect report, this will become just args . It'll be perfect forwarding. It'll be args ref ... And you'll no longer be able to format bit fields, I'm sorry. But it'll clear the way for formatting containers.
Great, thanks. I have another online question. If I'm doing buffered I/O and already have a buffer, is it possible to utilize it?
So vformat2 will always do this type erasure thing. So you do get some double buffering. We have done some benchmarks here, and Victor has also done benchmarks in libfmt, and the performance gains were pretty minimal from doing that particular optimization. And also, we have to have a way of discovering exactly how you are buffering. For example, some IO streams types are technically buffered, but we'd still want to use the small fixed size buffer because some implementations made poor choices on on how much buffering they were going to do. Or they need to do stuff to sync with stdio.
Cool. We have another question from online. How do you make sure the buffer is big enough?
So the fixed size buffer that we use is fixed size, and what we do is we know how big it is, and we write that many characters in between flushes to the output iterator. So once we've written 256 characters here, we just copy everything to the actual container that you're formatting into. We also do this when we're done formatting, of course. And then we can just start, again, outputting stuff to the beginning of our buffer. For the specialization for pointers, that one is specifically, when you're using that, you're opting into a somewhat dangerous feature where you have to make sure that the buffer you give it is big enough for any possible thing that could be formatted into that. So, for example, if you're formatting floats into it, like there's an actual maximum length of the float after being converted to a string. There's also a function in the standard that'll tell you the size of what you're formatting. And there's a function called format to n, where you can pass, this is the size of my buffer, and we'll stop when we get to that size, just like sn printf.
Great, thanks. And then I have two more quick questions from online. First one is from anonymous attendee. Is Victor Zevarach still involved with STD format?
Yes, he is. So I mentioned that he actually contributed some of the, so our implementation is directly based off his library. And he himself also contributed some code to our implementation. He is still involved in libfmt. I think I don't follow libfmt's development quite close enough to know if his number of commits into that library or anything has dropped off. But he's also quite involved in the standardization process for both the generator extensions, fixing various little bugs in std format, and working on some upcoming text-related features. For example, std print, which is like format, but for replacing printf instead of sprintf. All right. Thank you, everybody.